Imagine a server with many jobs waiting. Some are routine. One is urgent. If the repeated question is, what should run next, scanning every job again and again is wasteful. A priority queue is the structure built for that repeated question. In this video, focus on 4 ideas. First, what a priority queue promises. Second, why a heap has 2 rules. Third, how insert and extract change the shape. Fourth, why a heap is not a fully sorted list. A normal queue preserves arrival order. That is fair when first come should mean first served. But priority work is different. The next task should be the most important one, even if it arrived later. A priority queue stores items with priorities and makes the best priority easy to access. It does not promise that every item is sorted all the time. It promises that the next most important item is ready. A binary heap is a compact way to implement a priority queue. For a max heap, the largest priority stays at the root. For a minute heap, the smallest priority stays at the root. The exact direction depends on the question. The first rule is shape. A binary heap is a complete binary tree, filled level by level from left to right. This keeps the tree short, so moving up or down takes only a few steps compared with the number of items. The second rule is local order. In a max heap, every parent has priority at least as high as its children. Notice what this does not say. Siblings do not have to be sorted, and cousins do not have to be sorted. This is the beginner trap. A heap is organized enough to reveal the top priority quickly, but not organized enough to list everything in sorted order without extra work. It is a top priority machine, not a sorted array. Most heaps are stored in an array. The tree is a mental view. The array positions imply parent and child relationships. That is why heaps are compact, no separate pointer boxes are needed for the ordinary binary heap. To insert a new item, place it in the next open position so the complete shape remains valid. The new priority may be too important for that low position, so the heap repairs the order rule by moving it upward. Bubble up compares the new item with its parent. If the new item has higher priority, swap them. Repeat until the parent already wins or the item reaches the root. Only one path changes. Once the heap rules hold, peak is simple. The best priority is at the root. You can read it without scanning the whole structure. That is the point of maintaining the heap shape in the first place. Extract max removes the root in a max heap. That creates a hole at the top, so the heap moves the last item into the root position to keep the complete shape, then repairs the order rule downward. Bubble down compares the moved item with its children. In a max heap, if a child is larger, swap with the larger child. Repeat until the parent beats both children. Again, repair follows one path. The work follows the height of the heap. Because the shape is complete, doubling the number of items adds only one extra level. That is why insert and extract are logarithmic size path repairs. If you already have a messy array, you can build a heap by heapifying from the lower internal nodes upward. Each local repair assumes its children are already heap-shaped. The repairs cooperate from the bottom up. A useful surprise, building a heap from an array can be done more efficiently than inserting every item one by one. Many nodes near the bottom have tiny repair paths, so the total work is better than it first looks. Heapsort uses the heap as a bridge to sorting. Build a heap, repeatedly move the maximum to the sorted tail, then restore the heap on the remaining prefix. It sorts in place, but it is not usually stable. A sorted array makes the best item easy too, but insertion can be expensive because many items may need to shift. A heap pays less to update while still keeping the top priority easy. A heap is weak for arbitrary search. If the question is, where is this exact key, or show every item in sorted order now, the heap is not the right shortcut. Heap, fast top priority, not arbitrary search. A minute heap uses the same structure with the comparison reversed. Instead of biggest at the root, smallest is at the root. That is useful for shortest tentative distance, earliest deadline, or lowest cost. Priority queues appear inside bigger algorithms. Schedulers choose urgent work. Simulations choose the next event. Graph algorithms choose the next closest frontier. The heap is often the engine under that choice. Let us trace one insert slowly. Suppose the heap already has 72 at the root, then a new task with priority 99 arrives. We do not rebuild the whole structure. We place 99 in the next open slot, compare with its parent, swap upward, and keep going until the parent rule is true. Now trace extract. The root leaves first because it is the answer. The last item fills the root hole only to preserve the complete shape. Then bubble down repairs priority. At each step, compare with the stronger child, swap if needed, and stop when the local rule is restored. The array version is not a separate idea, it is the same tree packed tightly. Position 0 is the root. Nearby positions represent the next level. Parent and child positions can be computed from the index, so the heap gets tree behavior without storing pointer links. Here is the operation receipt. Peak is cheap because the top is already maintained. Insert and extract cost a path repair. Arbitrary search is weak because the heap does not organize every key globally. That receipt is what tells you when the structure fits. One reason heaps matter is that they become a subroutine. In Dijkstra-style shortest path thinking, the frontier keeps many possible next vertices. A priority queue repeatedly asks which tentative distance is smallest now. The heap makes that repeated choice efficient. Picture 4 jobs waiting: cleanup priority 20, report priority 40, alert priority 95, and backup priority 70. A heap does not alphabetize them or sort every job. It keeps alert visible first. After alert runs, the structure repairs itself so backup becomes the next visible winner. The parent rule may feel too weak at first. But for priority queues, local order is exactly the right amount. If every parent beats its children, no child can secretly outrank the root. The root is safe, even if the lower levels are not globally sorted. When you hear heap, do not picture a neat ranking from first to last. Picture a podium that is constantly repaired. The top spot is protected. The rest of the tower only needs enough order to keep protecting that top spot. Use a heap when the repeated question is top priority. Pause when the question is exact key lookup, sorted iteration, or range search. Those are different promises. The heap is not bad at them by accident, it simply prepaid for a different future question. Think of a heap as a tournament tower. The champion sits at the top. The tower is not a full ranking of every contestant, but it is carefully maintained so the current champion is always easy to find. Recap: a priority queue answers what matters next. A heap keeps that answer cheap with a complete shape rule and a parent priority rule. Insert bubbles up, extract bubbles down, and arbitrary search is not the heap's strength. Next, we will study trees that stay balanced. Heaps keep the best priority at the top, balanced search trees keep ordered search paths short.